So, welcome back friends, welcome to the third lecture on quantum field theory and canonical quantum entanglement. So, we have been looking at quantization of the scalar field essentially. We just started, okay, I should say that we have started at looking at canonical quantization of scalar field. So, what okay now what is we in the previous class we looked at what is canonical quantization. Canonical quantization is by taking writing the Lagrangian in terms of q, q dot and t and taking the variable q and deriving its conjugate momenta and imposing commutation relations on the variable and its conjugate momenta in terms of commutation relations, which we call as quantization conditions, Then I also on a separate side aspect essentially I took the example of harmonic oscillator. I did the example of harmonic oscillator, canonically quantized it and studied the spectrum of it, starting with the classical harmonic oscillator. I quantized it in terms of and then wrote it in terms of creation and annihilation operators and derived the entire spectrum of the quantum canonical harmonic oscillator. Okay, I should call harmonic oscillator, simple harmonic oscillator. Now we want to move to classical fields. We want to do the same example. We want to write a Lagrangian instead for a relativistic scalar field. In the relativistic scalar field, I will tell you the connection with what one has done in relativistic quantum mechanics, okay, in a second, but we want to start with the relativistic scalar field and then do canonical quantization of it. So, the procedure is standard. We have to start with a relativistic scalar field in 4 dimensions. In a relativistic scalar field in 4 dimensions, write down the Lagrangian of it and then see how does it look, meaning how do you want to write down its Lagrangian and so on. So, and then do apply the canonical quantization methodology which we derived just now essentially. Okay. Okay, let us start with the relativistic scalar field. What do we mean by? So, first of all we will stick to 4 dimensions. And the space time is Minkowski space time. Okay, eta mu nu, it is defined by a metric. So, one can you can work with your own metric essentially, there is no problem, but the metric I chose is particularly this for example, one example metric is this one. So, the space time 4 dimensional space time eta mu nu and eta mu nu is your Einstein indices essentially, mu nu are Einstein indices. They go from mu is equal to 0, 1, 2, 3, where 0 is the time component and 1, 2, 3 are the space component. As same thing, mu is equal to 1, 2, 3. Now, what we want to write down is something called, now we do not want to write down particles essentially, we want to write a field essentially. So, we want to write for a field which is classical. Classical field which is invariant under Lorentz transformations. Okay. Classical field, a scalar field phi, so it is a scalar field. So, which is invariant means it is a scalar field. The scalar field obviously is an invariant quantity and everything. So, instead of now for this the required quantity is not Lagrangian, it becomes something called a Lagrangian density, because I will tell you why in a second. And from the Lagrangian, which is a function of q, q dot and t, this becomes a Lagrangian density of phi and mostly del mu phi. Okay, del mu phi, and there is no okay. So, phi, because space and time indices are same, you cannot use phi dot, you have to use del mu phi. So, why we need a Lagrangian density? Because our action should be invariant under Lorentz transformation. And also our Lagrangian. So, instead of working with Lagrangians, we work with Lagrangian densities, so that the action S is defined as del mu power 4 of x, which is okay, which is all the 4 indices essentially x 0, x1, x2, x3, and the Lagrangian density, which is a function of del mu phi for the scalar field. If it is just a function of scalar field, this is the definition of your action. The Lagrangian density itself should be invariant under Lorentz transformations. Okay. The Lagrangian density itself should be invariant under Lorentz transformations. Okay. So, and its form will be fixed. Now, classical Euler Lagrangian equations of motion. So, which are given by sorry, I should write in terms of q. Okay. This gets transformed into so the Lagrangian equations of motion are given by this. So, they get transformed. This is the relativistic form. So, this is for a particle on the left hand side, it gets transformed to a classical field. The equation which is for a relativistically free particle, relativistically we did not mention whether it is free or not, relativistic field, classical relativistic field, the equations of motion look like this essentially. So, they get changed by this. Now, we had a conjugate momenta for every particle. Okay. For a field, it becomes a conjugate momenta field essentially. P I is equal to del L, okay. But this gets transformed to a field pi of x t is equal to del L by del phi, okay, by dot is equal to, that is it, this is what it becomes essentially. Okay. Now this is del L by, because this is for the scalar field, this just becomes simple essentially. So this is the definition of the conjugate momenta field. Okay. Okay, conjugate momenta field. Okay. So we have defined equivalence for each quantity. Now with this we can define, so from a particle we are slowly moving towards the field. Okay. So from particle we are slowly moving towards the field, and so okay, the conjugate and everything. With this I can define the Hamiltonian. Now I can define the Hamiltonian density. In the Hamiltonian we had Pi Qi dot minus L. Now instead I have the Hamiltonian density. Okay, let me write down the equation first. So Hamiltonian density is equal to a curly phi essentially, which is given by phi pi dot, okay, minus L. Okay. So this is a function of okay, the Hamiltonian density is a function of h, is a function of pi of x, pi of x. Now one has to be a bit careful here, okay, because okay, if you write the full Hamiltonian, okay, if you want to write the full Hamiltonian, so you can write the Hamiltonian to be density of del mu of x h of pi phi. Okay, this is how you define your Hamiltonian density, and okay, you can write it in a covariant fashion and so on, so essentially. Okay, this sort of sets the full Hamiltonian. Okay, I should be careful here. I think it should be d cube of x. Okay, this set of sets our movement from particle to field theory. Essentially, we have defined the Hamiltonian, we have defined the conjugate momenta, all in terms of the relativistic particles, essentially in terms of relativistic fields. So now I also defined the Hamiltonian equations of motion just for is given by phi dot of x t is equal to del h by del pi and pi dot of x t del h by del phi. Okay. So you have the equivalents of exactly like so there is some sort of a field particle duality or equality. So wherever there is a particle you replace it with a field, and just make sure that they are covariant in the sense that instead of Hamiltonians you replace it by Hamiltonian densities, instead of Lagrangians you replace by Lagrangian densities, and lo and behold you have roughly you have the equations of motion, you have the both the Lagrangian equations of motion, the Hamiltonian equations of motion, and now also the conjugate momenta and so on. So with this, what we have shifted is we have transformed from particle description of the Lagrangian method, essentially Lagrangian method, to a field theory, classical field theory description of a Lagrangian and Hamiltonian methods. So the description proceeds by replacing the q, which is nothing but your generalized variable, in terms of a field, essentially, which is a, here we have taken a scalar field, in terms of the scalar field phi, and then proceeding straightforwardly, and Lagrangian you replace it by Lagrangian densities, so that they all become invariant under Lorentz transformations, and the Hamiltonian in terms of the Hamiltonian densities, and you can derive the entire field theory consistently. Now we have a classical field described by the above set of equations, essentially. Okay, it all we have to write down is a classical Lagrangian, okay, density, and then impose canonical quantization conditions. Okay. Now I will start with a simple field, essentially. I will start with a Lagrangian density of a simple scalar field. Scalar field, I have been mentioning it, it is an invariant quantity under Lorentz transformations. So that is what I will start with. I will start with something called a real scalar field. Okay. So the Lagrangian is equal to 1 by mu del mu phi minus m square by 2 phi. The Lagrangian of a real scalar field is given by this particular fashion. How do you know this is the Lagrangian? Because the kinetic term is nothing but the Lagrangian density is del mu square. So it should go as del mu square, okay, del mu phi and del mu phi, instead of writing it in terms of and the kinetic term is not just phi dot square essentially, but it has to be del mu, as we have seen the moment it transformed into a field from a particle. And so this is the kinetic term. I will tell you why there is a half comes later on, essentially. And the potential, I did not put any interactions, it is a free field, okay. This is called a free field. So the only other potential term which comes out is the mass term, which is exactly like m square by 2 phi, okay. Now this expression, okay, this expression is very well known to us, essentially this is well known to us. So this is called the Klein-Gordon real Klein-Gordon, okay. Real Klein-Gordon, this is real Klein-Gordon field. We have seen this in the relativist. I will tell you the connections in after quantization, okay, after doing the real Klein-Gordon field. Okay. Now before going further, I will introduce, we will do something more. What is the action for this field? For this field, S is equal to, okay, integral d mu power 4 L phi del mu phi, okay. Now I know what is L is del mu 4 is equal to half del mu phi minus m square by 2 pi square, okay. Now what is the mass dimension? Now consider, we go back to our h cross is equal to c units, which are natural units. In these units the action is dimensionless. So the action is dimension. There are various reasons why it should be dimensionless in this unit. Okay. So the action is dimensionless. So the left hand side has dimension 0. Okay, on the right hand side you have mass dimension -4 coming from d bar 4x. So dx has a mass dimension -1. d power 4x gives you -4 mass dimension. d power 4x means dt d by dx. So this is dx is nothing but d by dx, right. So d by dx has a mass dimension. X goes as a g power GeV -1 essentially. d by dx goes as GeV -1 essentially. So this is goes as -4. d power 4x goes as -4 mass dimensions. So the Lagrangian density phi del mu phi should be of mass dimensions 4. So this representation is mass dimension. So this notation stands for mass dimension. So on the left hand side you have 0 mass dimension. So on the right hand side you should have, in the integral you have a -4 mass dimension. So if you want to have 0, the Lagrangian should be having +4 mass dimension. This is all true in 4 dimensions. That means 4 dimensional space and time essentially. In the day now we know 4 dimensions for space dimensions should have, the Lagrangian should have dimension 4. So with this we look at del mu phi okay 1 by 2 m square phi square. M has mass dimension 1, del mu has mass dimension 1 because it is it has a mass dimension 1. It's a derivative of space essentially. Del by del x has a dimension 1. So this gives us, putting this back into this, the total Lagrangian has mass dimension 4. So that means 1 plus 1 2. So this implies phi has mass dimension 2. I hope you all understand. Oh sorry, phi has mass dimension 1, sorry 2 phi has mass dimension 2. So phi has mass dimension 1. Okay. So each term is of dimension 1 essentially. So each term is of dimension 1. This is a phi square is phi times phi. So each phi has mass dimension 1. So the mass dimension of the scalar field is 1 essentially. It has 1 mass dimension. We now then move to derive the equations of motion. The equations of motion. So this is important because this will be very important in field theory. We should know the mass dimensions of the fields we are dealing with. So this has a the scalar field has a mass dimension 1, and we will see the scalar the fermionic field, what is the dimension, the vector field, so on. So the equations of motion, I think there is no big surprise. This just becomes the Klein-Gordon equations of motion. Okay, now we have set up the entire thing. Now we proceed on to do the canonical quantization of this particular field essentially. We now proceed now you should, I am doing it slow this one because the first one I will do it slow, and as we will see for the fermion and so on, so things become slightly complicated. So I want all of you to do the first one very slowly and carefully essentially. Okay. So for this the first step is to define the conjugate momentum field. So, the conjugate momentum field phi of x will be del L by del phi dot, that is nothing but phi dot of x. Okay. The conjugate momentum field is nothing but del L by del problem. With this we can write down the Hamiltonian, okay, the Hamiltonian density okay, let me write where I wrote the del mu in terms of nabla square, del phi square and del by del t square, which is phi dot square, which has a minus sign, and that minus sign gets cancelled, and that is the reason why we get a plus phi dot square essentially. So, you get a plus phi dot square essentially. Okay. Now, the symmetries of this theory are essentially, this is Poincare invariant, it is invariant of okay, it is invariant under, okay, we can it does not have any electric charge and so on. So, what we have to do is, if you want to impose what are the canonical quantization conditions on this particular thing. So, the theory is the Lagrangian, okay, let me, instead of the Lagrangian is Poincare invariant Lorentz. Poincare means Lorentz invariant plus translational invariant okay. The theory is Poincare invariant, and now we are ready to impose the canonical quantization. Okay, this is very straightforward. Okay, and for that we also derived your our conjugate momenta essentially. So, we now impose, now okay, I will come to that condition in a second essentially. So, we now impose the canonical quantization conditions. So, how did we impose last time? Essentially we just imposed P q is equal to H cross, essentially that is what we did. So, the same thing we have to do, essentially we have to define phi and pi, okay, let me write it down explicitly, of x t, pi of x t is equal to I del cube x minus x pi. Now, here I made a big step essentially without, because it is a relativistic theory, I made a big assumption without even discussing or detailing it to you. I assumed both phi and the conjugate momentum are to be at the same time, essentially t at the same time satisfying this conjugate this commutation relation essentially. Okay. This commutation relation should be satisfied at the same time. So, that means that these are called equal time canonical commutation relations. So, these are called equal time canonical, but the equal time, sometimes you can give it an ET-CCR or something we can call it, but anyway these are called equal time canonical. So, this is an important point that you are imposing, because we are in a relativistic theory, we are imposing it H cross is equal to 1, C is equal to 1 and so on. So, we are imposing that they should also be at equal time. Okay, this is important point essentially. So, we have other two relations of phi at x t and phi at y t should be equivalent to pi at x t comma pi at y t. All this should be equivalent to 0. They should commute. The fields should commute at different space time points. The conjugate fields also should commute, conjugate moment of fields also should commute at different space time points, but the field and its conjugate momentum field will not commute at different space time points, but at equal time, Okay. This is the first step. Now, we can write the Hamiltonian in terms of, now you can see the Hamiltonian already, we can see it has a quadratic form, okay, in terms of phi dot pi square and q square. So, this should remind you of the Hamiltonian of the harmonic oscillator, So, in the next class what we are going to do is how this gets related to the harmonic oscillator. But for the present, just remember this, we have done the first step of taking a scalar field and then imposing the quantization conditions on the scalar fields. So, these are called equal time canonical commutation relations, and now we will see further how these effects can be represented in terms of particles and how the particle spectrum arises in a quantum field essentially. Okay. I will stop here for this lecture and I will see you soon in the next lecture. Thank you very much. Welcome.